And you know it, clamp your ham. Welcome to video 31. We're going to be looking today at stress equations or stress transformation stuff. We're going to be talking about maximum stress still, but we're going to be doing it faster, better, stronger. I don't remember the rest of that. It's better, faster, stronger. So we're going to be, here's what we've done so far. The big takeaway from the previous video was these ideas of maximum stress. So when we talk about the principal stress related to maximum normal stress, we have an equation to calculate that. And when that happens, right, we have no shear stress. At our maximum normal stress, we're able to find an orientation where there is no shear. So we have two possible values or two principal stresses, sigma 1 and sigma 2, representing the x and y direction respectively on our rotated element through an angle of theta p1, basically to get to that angle of maximum stress. How much do we have to rotate to get to the maximum stress? Orientation. We did a similar thing with our maximum in-plane shear stress. It's in plane just looking at that two-dimensional image. That we will talk about absolute maximum shear in like a three-dimensional sense in our last video in this chapter, but everything we are doing is essentially going to be two-dimensional for the most part. And then we found that when we have that orientation for maximum shear stress, there is still a normal stress. It just happens to be that average stress, sigma x plus sigma y over 2 that we had on our original element. So those are kind of the big two takeaways. We're going to keep working with those ideas, but we're going to get to them faster. And we're going to talk about stress transformation in a slightly different way. So that's our goal for today, is to be able to create and apply Mohr's circle to determine maximum stress, and also to figure out the value and orientation of the principal stresses a little bit quicker. And that's going to be basically our goal. So we're going to derive Mohr's circle, starting with our formulas for stress at a generic angle theta, right? So a couple things we want to take away from here. We're going to notice that this first term here in our sigma x prime equation is going to be our average stress. So we're going to acknowledge that, and we're going to kind of move it over to the other side of the equation, because if we do that, we have a bunch of sines and cosines that are going to be left over. And we can go about squaring and adding both sides. So when we have all of the sines and cosines left over and we square them, we're going to end up with cosine squareds and sine squareds. And we're going to have things in such a way that we can add things together and the cross terms are going to cancel out. And we're just left with a bunch of cosine squareds and sine squareds, which we know that cosine squared plus sine squared is equal to 1. Hopefully you said that anyways. It's just like some sort of Dora the Explorer video. This entire class. So we are going to move that sigma average over. Then we're going to square and add both sides. So we have sigma x prime minus sigma average squared and tau x prime y prime squared. After you do that, and oh, whoops, that's not what I wanted, but we're going to do that and we're going to add them together, which is literally what I said. So we're going to put that up here. Great. So if we do that, what's left over then? After we square and add everything together, the sine squareds and cosine squareds go away. We end up with sigma x minus sigma y over 2 squared plus tau xy squared. Curious, especially curious considering that this first term is the equivalent to, and I will prove it, sigma x minus sigma average. Because if we have sigma x minus sigma average, that's minus sigma x plus sigma y over 2. So we end up with sigma x minus 1/2 sigma x, which is positive 1/2 sigma x, and then minus sigma y over 2. And that becomes that first term here. So you can see that we end up with something equivalent on both sides of our equal sign, except one is for the rotated bit and one is for the original stuff that we looked at. So what we can kind of do and notice is the fact that this here we can call r squared, and we get what is going to be essentially the equation for a circle, right? You have, I think it's x squared plus y squared equals r squared, right? So we can get the equation for a circle here with sigma and tau as our axes. And it works at sort of any generic bit. So this is the equation for a circle. The other thing I think that's interesting is this also validates Pythagorean theorem. So this radius is actually going to be the hypotenuse of our triangle. So let's get that set up, right? Let's kind of derive this here. I'm going to copy this generic equation over. So we have r squared is going to be sigma x minus sigma average squared plus tau xy squared. So let's try to make something from this here. I'm going to sketch some axes. For these axes, in order to have the clockwise and counterclockwise rotation stuff match up, tau is going to be positive in the negative y direction. I don't want that line there. There we go. Sigma. Okay. So, right, we've got a couple terms to kind of match out here. If I identify my center of this circle, right, based on circle equation stuff, well, let's put our state of stress on here, right? So this is basically we're looking at sigma x, sigma y built in here with our shear as well. So our initial state of stress is going to be given on we're plotting sigma x and tau. So this we can just say is going to be our point A, which is going to be our initial state of stress. We're going to have these labeled on a diagram on your equation sheet, which is why I'm labeling the same letters now. Initial state of stress, which is given by sigma x, tau x, y. So I'm going to take those two values from my initial square, and I'm going to put those on just on the graph somewhere, right? And I know that the sigma x minus sigma average bit is going to be one side of a triangle, and the tau xy bit is going to be the other side of a triangle. So this is going to be my tau xy, which means that this distance is going to be sigma x minus sigma average, because those together are going to form a right triangle that's going to have that hypotenuse r. Which means that if this is going to be our generic triangle, that sigma average are is going to have to be the definition of where the center is, right? So our center is going to be defined, center is going to be defined as sigma average with no tau. Because this R here is going to trace out a circle. If I sweep this around, if I rotate this element through some angle theta, right, we end up with a circle. Because any state of stress, any of the sigma x primes, tau x prime, y prime stuff has to exist at that same R based on our equation. All stress has to exist at this same R. Oh man. Okay. Right. So we get a circle because all of our stresses have to exist at that R. It's kind of neat. So there's a lot that we can end up doing with this. It actually allows us to map out a bunch of different things on our diagram here. So we can think about rotating a particular direction, or we can at least look at points on this circle. So where the circle is going to be crossing our x-axis, it's bothering me that the circle is not circle. I'm gonna not make it worse though. I'm gonna try once and we're gonna just see what happens, and I'll take whichever one I like better. I like the smaller one better. This circle, where it crosses our x-axis this first time over here, this is gonna be all normal stress, no shear stress. This happens to be our first principal stress, sigma 1, which we can see based on this diagram is gonna end up being sigma average plus my radius, which if I write that out, because I can, if I sweep my radius up, right, it's those two things along the x-axis. If I write that out, that's sigma x plus sigma y over 2 plus the square root of sigma x minus sigma y over 2 squared plus tau xy squared. And we already know that that second term is just going to be our sigma x minus sigma average. So we're going to use that from now on. Um, but that is the same equation that we derived the other day, right here at the top. Sigma x plus sigma y over 2, that's sigma average. And then plus or minus what's inside that square root is our radius. So it's plus or minus the radius of that Mohr circle. What? Okay, what does that mean about sigma 2 then? Because there's that plus or minus. What's the sigma average minus the radius? That's going to be this side of the circle, so that's going to be our sigma 2. So those are our two principal stresses that we have. Sigma average minus the radius. You can see how it's a lot easier to conceptualize the type of stuff that we're doing here, but not only that, be able to get to the equations that you need for principal stresses. Because if we want to rotate from this initial state of stress to the maximum, uh, to the principal stress, we want to go through, and this is going to be 2 theta here, because of the 2 theta in our trig stuff that we had before, right? So we want to go through 2 theta. This is actually going to be 2 theta P1. So that's our rotation to our principal stress. And so we can get that tangent of 2 theta P1 is going to be the opposite tau xy over the adjacent sigma x minus sigma average, which has that built-in 2 in it that was in our numerator before. What? Whoa. So more circle is just going to be kind of a quicker way of doing our analysis rather than having to think about these really big, long, complicated formulas. We're going to be able to kind of work through stuff here. And if we want to go to the maximum stress in plane, well, our maximum tau is going to be at the bottom because that's where it's going to be the largest. Uh, and we can see that that is just going to be equal to our radius, which it is if you go back and look at our previous equation. It's that square root of sigma x minus sigma y over 2 squared plus tau xy squared. And at that point, we don't have a sigma of 0. We have that sigma as sigma average. So we can see the way that that is going to essentially be playing out and how we can kind of move from one of these to the other. We have this, it's 90 degrees on this circle because everything's 2 theta, but you can think about that as being 45 degrees in the actual physical rotation of our uh, differential element, right? So 90 degrees in the circle is 45 in real life. We can see that they're separated by that. We can see that sigma 1 to sigma 2 is 180 in our circle, which means it's 90 in the actual thing. So I rotate the square 90 degrees. It looks exactly the same. So that is all working out. All of the stuff that we built conceptually with how these stress elements are going to work is reflected here in Mohr's circle. Kind of neat. So let's summarize. I have the picture from the textbook, which essentially just shows all of the stuff that we just looked at, as well as a generic element P, which we can just find those pretty easily as well. So the first thing I want to do, acknowledge our sigma average is sigma x plus sigma y over 2. We find the center by doing the sigma average and 0 for our shear stress. So that coordinate is going to give us our center. We map out our sigma x, tau xy as our initial state. So those coordinates represent our initial state. You get those two things down first. Then we're going to calculate the radius. So that's all basically step 1 and step 2. So this is step 1. Step 2 is our radius. So we're going to get that by doing sigma x minus sigma average squared plus tau xy squared. And then we get whatever else it is that we need. So big picture, big items on these on this circle. B is going to be our sigma 1, which will then just be sigma average plus or minus or plus R for sigma 1. D on the other side is going to be our sigma 2, which is going to be sigma average plus R. And then our 2 theta P tells the angle of rotation to principal stress. E and F represent both our tau max in plane. Now, it doesn't really matter which way you kind of go to those because they end up being the same and the sign doesn't really matter that much, right? It ends up being the same stress element. We have 2 theta S then is basically the angle to max shear. And the reason we orient the axes like this with tau being downward is so that the direction of theta tells us which way we have to rotate our element, which way we have to rotate our element. I've got 2 examples for us to look at, and that's going to be it for this video. So let's jump into our first one. This is example 9.7. Due to the applied loading, the element at point A on the solid shaft is subjected to the state of stress as shown. We want to determine the principal stress is acting on that point. So we see an element here which is undergoing a compression along the horizontal direction of 12 ksi, and we have a shear stress acting downward on the right side of 6 ksi, which means we need to remember what our conventions are for positive directions. So that way we can get our initial state of stress. Sigma x and sigma y are both positive as they're directed away from our stress element. Shear is positive if it's directed up the right side or to the right on the top side. Which means then our initial state of stress here, we're going to have sigma x as negative 12 ksi. Sigma y, because there's none depicted, is going to be 0, and tau xy is going to be, since it's down on the right face, negative 6 ksi. That's our initial state of stress element that we are working with. Our first step for this problem is going to be to label the center and our initial state. Label center and initial state. So you'll see how easy this is here. Let's go. So we are going to be dealing with some negative numbers. So I'm going to draw my axes over here a little bit more. And then our center is going to be at sigma average. So we want to calculate sigma average. Sigma average is going to be sigma x plus sigma y over 2. So that's going to be negative 12 KSI plus 0 over 2. Our average is going to be located at negative 6 KSI. Trust me, I know you could just do those numbers and be good, but it's so much clearer and faster to map stuff out on the graph, and I'm going to show you why. Because it really helps us kind of avoid some of those more complex equations. So we've got our sigma average mapped on our graph here. This is going to be our center. So I'll label that point C. Next, we're going to put on our initial state of stress. So that's sigma x tau xy as my coordinates, which is going to be negative 12 and negative 6. So we want to go out negative 12 in the x direction and then negative 6 in the y direction to get my initial state of stress. That's going to be point A. You actually probably don't even need to draw out the circle for all of these, but it still is nice to look at, right? So I've got that, got my initial state of stress. Step 2 is the radius, which is going to connect points A and C. And the point of doing the circle is like I can just look at this now and know what all of the values are that I need. It's going to be the square root of 6 squared plus 6 squared, right? That's it. That's all this is. You can go through the formula if you want still, is fine. Sigma x minus sigma average all squared plus tau xy squared, which is going to be negative, so the square root of negative 12 minus negative 6 squared plus negative 6 squared. Right? Yes, lots of negative signs. So that is going to give us a radius of 8.49 KSI. So mostly the triangle, I think, is the part that helps me the most. We don't really have to finish depicting the circle. We will anyways, because we're bad at circles. I'm just trying to get out of doing stuff I'm bad at. Okay, that was better than I thought it was going to be. So you can see a couple different spots here. Mostly the circle is to help us figure out which or like direction we have to be going. So that's why it's worth maybe sketching out. But you've got sigma 1 and sigma 2, which you can go ahead and label if you want. That's probably going to be the next stress. We want principal stresses at this point. So step 3 is going to be principal stresses. It doesn't ask us to find maximum in-plane shear, but guess what? We already have it, right? Because that is our radius. So if we wanted it, we already have it because that's the radius that we have here. Isn't that handy, right? But if we want the principal stress for step 3, sigma 1 is going to be the sigma average plus R, which is going to be negative 6 plus 8.49 KSI, which is going to be 2.49 KSI. And you can see how already having calculated the radius values and our sigma average values, like the rest of these calculations, even though they're really long equations, uh, are really as simple as our sigma average plus or minus r. So sigma 2 is going to be -6 minus 8.49 KSI, which is going to give us 14.49 KSI. So now we now have both of our principal stresses. We know what those magnitudes are going to be. And if we want to get our element to a point, we want to know what the orientation is going to be. The closest orientation for maximum stress. We can see that it's going to be a counterclockwise rotation. So usually we can get the orientation for this as well. Tangent of 2 theta p is going to be the opposite. So we've got -6 over the adjacent, which is also -6, which is going to then give us theta p as 2 theta p is going to be 45. So 45 degrees over 2 is going to be 22.5 degrees counterclockwise. We only have to go counterclockwise because if we go counterclockwise, even though our x-axis is going to be the sigma 2, our y rotated axis is going to be sigma 1. So we're rotating 22.5 degrees. This is going to be sigma 2, which is negative. I should draw it negative. Sigma 2 versus a smaller tension for sigma 1. Sigma 1 is always going to be the more positive value, not necessarily the bigger one. It depends on what we're looking at. So you can see that we've got a lot of compression at 22.5 degrees and then a little bit of tension. But that's it, right? That's Mohr circle. That's the kind of stuff that we're going to be doing in the rest of this video. We will do I have one more simple example here, just to kind of get comfortable with this. And then in our next video, we will do at least one example all the way through from the beginning of like, here is internal loadings, go. Uh, and then in the video after that, or maybe the next video, depending on timing, we'll do one from here's the whole system with forces, find internal loadings, blah, 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 blah. So we're going to do some practice all the way through and combining the chapter 8 and chapter 9 stuff here. But one more example of Mohr circle, which might be good for you to do on your own. So I'll read through this, and I want you to kind of follow the process, see what you can do here, just having seen it once. So we want to, for this problem, determine the equivalent state of stress of an element at the same point, which represents the principal stresses and what the orientation is. So we just want to find out what the maximum normal stress is, as well as how much we have to rotate to get to that point. And we also want to figure out the maximum in-plane shear and how much we want to rotate to get to that point. And you can sketch these out afterwards. I did not sketch them out, but you can. So go ahead and pause, see what you can do here with this. Okay, so let's look at our initial state of stress here. Sigma x is going to be 125 megapascals. Sigma y is going to be -75 megapascals. Tau xy, because it's directed downward on the right face, is going to be -50 megapascals. So we've got those sign convention down. That might have been the one thing that you had to look at for the previous slide. But step one here is going to be to identify the center and the state of stress. So the center is going to be at our sigma average 0 coordinates. So sigma average is equal to our sigma x plus sigma y over 2. So that's 125 plus negative 75. So that's going to be 50 over 2, which is going to be 25 megapascals. And my initial state of stress is located at sigma x tau xy, which is going to be at 125, negative 50. So we are going to map that out. I'm going to do this over here this time. Sigma is on our horizontal x-axis. Tau is on our downward y-axis. Our center is going to be located 25 along our horizontal axis. And then I left space because sigma x is like 100 away from that. It's at 125, so it's going to be over here-ish. And then I want to go in the negative tau direction, 50. So somewhere about here, I would say. So it's going to be negative 50. I know that this whole direction here is going to be 125 for my coordinate for A in the X direction. I'm going to connect those by a single line, which is going to represent my radius. And I'm not even going to draw a circle for these because space, but you can kind of imagine, right, the circle there wrapping around it. It's a big circle for this one. I want to fit it on the page, so I'm not going to sketch that out. But step 2 is going to be to get our radius. So we have r equal to, and I can just look at this and Pythagorean theorem this. That's the benefit of being able to have this kind of sketched out here. So it's going to be 125 minus 25 squared. That's our sigma x minus sigma average. That's going to be plus negative 50 squared. That's our tau xy. This is going to give me a value of 111.8 megapascals, which is my tau max. So part of part B is already done, right? Because our tau max in plane is our radius. But I want to use that for my principal stresses. So we'll jump into step 3 for our max stress. Sigma 1 is going to be the average plus my radius, which isn't that much. So that's going to be what we have, 25 plus 111.8, which is going to come out to be roughly, we're just going to round here to 137 megapascals. And then sigma 2 is going to be sigma average minus the radius, which now you can maybe see why I didn't sketch out the circle. 25 minus 111.8, which is going to be negative 86.8 megapascals. So both of those are done. If I want to get to that element, I can see my triangle right here to get to that horizontal side. So I want this to theta p right here to my principal stress. So the tangent of 2 theta p is going to be negative 50 over negative or over 100, which is going to end up giving me theta p as 13.2 degrees. So I get that. This is going to be clockwise rotation based on what I can see from my circle. And if we want tau max in plane, that's just our radius, which we already have. So that's going to be 111.8 megapascals. And we also know that the normal stress at that point is our sigma average, which we already have. So it's nice that like by the time that you get to our maximum shear stress, we already have everything. We do know that we can go another 90 or 45 degrees to get to our maximum shear here. So we're gonna, well, we want the complementary angle to theta s to get to our tau max shear. So 45 degrees minus 13.2 degrees is going to be 31.8 degrees. And we know that that's going to have to be counterclockwise based on our diagram. Ta-da! So that's how you get everything. Look at how little math and equations there is on this page. Having the circle and offloading some of that is super helpful in terms of keeping track of all the things that you do. It's going to kind of speed this part up. So this is why we're tagging chapter 9 into chapter 8, because this is really just like an extra little bit on there that's super relevant to the stuff we want to do in mechanics and materials, but it's not much more work on top of what we've already been doing in chapter 8. So it's good to look at all of those together because we're going to see all of those types of things together when we are solving problems, which we will jump into in the next video. So I will see you there.